Hello, today we're going to start section 2.1. This is the beginning of chapter 2. This is now the official beginning of calculus, and all of calculus is based on the idea of limits. Okay? So let's continue with your guided notes. These are posted on Blackboard. You can print them out and take notes as we go along. So the limit, when you see this kind of notation here, this is read as the limit of f of x as x approaches 3 equals 10. Okay, so that's how you read that. A one-sided limit means you're only approaching from one side. See, if I say x equals 3, if I just say x equals 3, that means I'm approaching from the right and the left. But if you see a 3 with a minus up top in the superscript, that means x approaches 3 from the left. And if it says x approaches 3 plus, that means x approaches 3 from the right. So what do I mean when I say x approaches 3 from the left? That means we're getting closer and closer to 3, but from the negative side. So my numbers will be 2.9, 2.99, 2.999. And then from the right, they'll be 3.1, 3.01, 3.001, and so on. Okay? Let's do an example. So if I want to find the limit as x approaches 0 of this function, now notice, I cannot plug 0 right into the function, because if I do, I get 1 over 0, and that's undefined. That's why I need to take the limit, because this function is not defined at 0, but it is defined close to 0. So it says by table, so let's make a table. So I'm going to choose x, and let me call this f of x, okay? Or let me write it out for you. 1 plus x to the 1 over x. Okay. Now let's think about x equals 0. Okay. If I approach 0 from the left, what numbers am I going to be looking at? So from the left, I know it's negative. So it'll be like negative 0.1. And then let me get even closer, negative 0.01. And then negative 0.001. Okay, and then from the right, I'm looking at positive 0.1, positive 0.001. Whoops, this is not, should not be here. I need to make another table. Again, 1 plus x to the 1 over x. This is, and you can continue this table, make it a long table, 0.01, positive 0.001, and then oops, I should have started with 0.1. That's okay, it doesn't make a difference what values you choose, as long as you try to get close to it, okay? Alright, now there's a way to do this in your calculator very nicely. So I want you to go to your calculator, type in y equals, and let me delete all this stuff from before. And you want to type in parentheses 1 plus x raised to the 1 over x. Okay, if you might have to put the 1 over x in parentheses. And then I want to go to second table set, that second window, and I want the independent variable to be ask. Okay? And then I'm going to go to second graph, which is the table, and now I can type in these values that I need. So negative 0.1, and then y1 are these values that I plugged in for, or is this function that I plugged in for y1. Negative 0.01, negative 0.001. Okay, and then on the positive side, I have, well, let me write these down. 2.868 it was, I think. (868-732-7196). And then for the positive side, let's plug in these values. So I know my positive values are, I start at 0.01, 0.001, and then 0.0001. Okay, that's 7048. That's 2.7048, 2.7169, and 7181. And those are the values I have. So if you look at these, what number am I approaching, right? 2.7196, that's roughly 2.72, 2.7181, that's also roughly 2.72. So I can say here that the limit approaches this thing, approaches or equals roughly, let me put approximately, squiggly equal sign, 2.72. Okay, so that is what it approaches. And that is actually a decimal, it's not a multiplication sign. Let me fix that. 2.72. Okay. It says, note in the above example, we could not simply substitute 0 in for x. Sometimes direct substitution, oh, that should say substitution, sorry, that's a typo, is possible. The rules of limits will let you know when to use which method. Okay, so a limit of a constant is that constant itself. Limit of x to the n, you can plug in c itself. If you have a square root or a cube or any kind of root, you can plug in the function itself. Then you have a limit of a sum is the sum of the limits. Limit of a difference is the difference of the limits. Okay. So let's do an example. Okay, right here. So here I have a difference and a sum. So I know the limit of a difference is the difference of the limits. Limit of a sum is the sum of the limits, like I have up here. So I can go ahead and plug these values in directly. So this is going to be the limit as x approaches 3 of 2x squared minus the limit as x approaches 3 of 4x. Now this is the first time we're doing this, so I'm just writing all the steps for you. You don't have to write this intermediate step when you do your homework. Limit as x approaches 3 of 1. Okay? So here I'm taking 3 and I'm plugging 3 directly into the function. So that's 2 times 3 squared minus the limit as x approaches 3 of 4 times x. That's 4 times 3 plus 1 will always be 1 no matter what x is, right? So x can approach 3 or 5 or 10, 1 will always be 1. So then that is equal to, that goes like this, and then it's equal to 3 squared is 9 times 2 is 18 minus 12 plus 1, which gives me what? 6 plus 1, 7. So my answer is 7. Okay? So as x approaches 3, this function approaches 7. So we can even check that on the calculator, right? So we have 2x. So let me delete this. We have 2x squared minus 4x plus 1. Okay, and I want to graph it. So let's do zoom 6. Oops, something happened here. Let's see, y equals 2x squared minus, did I do minus? Minus 4x plus 1. Graph it. I think I know what's going on. Let me go to my stat plot. Sometimes if this happens, you just have to kind of troubleshoot, right? And my plot 1 is on. I want to turn my stat plots off. So when you're doing algebra, you don't want any of the statistics stuff on. Now let's graph it. There you go. So when x is 3, so let me do, whoops, graph trace 3, y approaches 7, right? And that's from the right and the left, y is equal to 7, which is what this is showing here. So here direct substitution is possible. Sometimes you have to simplify, right? So if I plug 1, let's look at this function here. If I plug 1 in directly, I'm going to get 0 in the denominator. I'll get 0 in the numerator too, and that's not defined. So I need to simplify this. So how can I simplify this? I'm taking a limit, so let me write this as x plus, and x squared minus 1, if you remember, is a difference of perfect squares. So it's x plus 1 times x minus 1 divided by x minus 1. Okay, and then your x minus 1s are gone. So you're left with just the limit as x approaches 1 of x plus 1. Okay. Now we can do direct substitution. Now I can plug 1 in, and when I plug that in, I get 2. Okay. Let's look at example 5 in your book on page 83. So here is page 83, example 5. This is for the piecewise linear function. So when x is less than or equal to 3, we're on the line x equals 1. That's this line right here, or x plus 1. And when x is greater than 3, we're at 8 minus 2x. Now notice, at 3, when x equals 3, we're on the line x plus 1. Okay, so that means we're on this line. And that's why you have a closed circle here. And when x is greater than 3, 8 minus 2x is not defined. So at 3, you have an open circle here. Okay. And how do they know what the y value is? Well, if you plug 3 into here, 8 minus 2 times 3, whoops, is 8 minus 6, which is 2. So at 2, there's an open circle. Okay. And then x plus 1, that means 3 plus 1 is 4. That's defined, so it's closed at 4. Okay. All right. So I don't expect you to graph these by hand necessarily. You can use your calculator, or you can the graph will be given to you. Okay. So let's look at the limits. The limit as x approaches 3 from the left. So what you want to do is put your pencil on the graph, and as you get closer and closer to 3 from the left, the y value approaches 4. Okay, so the answer here is 4. How about as x approaches 3 from the right? So you put your graph, or you put your pencil on the graph, and you approach 3 from the right. So my y value approaches 2. It doesn't equal 2, but it approaches 2. Okay, that's what the limit says. It approaches 2. So at one side it's 4, the other side is 3. So as x approaches 3 from both sides, it's not the same number. So we say does not exist, or undefined. Okay? So this is what this solution tells you. 4 from the left, 2 from the right, and the two one-sided limits both exist, but they have different values. So the limit does not exist, right? It's not one number. So that's using the graph. You can also do this problem using the algebra, right? Using the function itself. So when you plug 3 into the first part, you get 4. When you plug 3 into the second part, you get 2. And since 4 and 2 are not the same number, you know the third part doesn't exist. Notice that the two methods found the same answers. Okay? Alright, let's go back to your notes. So that was example 5 in your book. Limits involving infinity. Okay, so this is saying the limit of a function as x approaches maybe positive infinity, or it could be negative infinity. Okay, means the values of the function become arbitrarily large. Limits involving negative infinity means the values become arbitrarily small. For rational functions, finding limits is the same as finding asymptotes. So let's look at example 6. So here is example 6 on page 84 in your book. It says, describe the asymptotic behavior, right? Asymptotic behavior. Where are the asymptotes of this function using limits involving plus or minus infinity? So what they've done is they've graphed the function below, okay? At 2, if I try to plug 2 into this function, you'll know I get 0 in the denominator, right? So something funny is going on there, and we know when you graph it, we have a vertical asymptote there, okay? So you can write that the limit as x approaches 2 from the right is positive infinity, and the limit as x approaches 2 from the left is negative infinity. Okay, again, this is shown in your book. Okay, and you can read all this. Then the example continues. Now what happens, and now I also have a horizontal limit there, horizontal asymptote there. So the limit as x approaches infinity of the function becomes 3, and the limit as x approaches negative infinity of the function becomes 3. Okay, so when we say limits involving infinity, let me go back to your let me go back here. Let's read this first. To say that a limit exists means that the limit is a number, and since positive and negative infinity are not numbers, a statement such as the limit of f of x as x approaches c is infinity means the limit does not exist. So we know you can never hit infinity because infinity is not a number, but you still want to write the limit is infinity or the limit is negative infinity. Okay? So when it says limits involving infinity, or if it talks about end behavior, you want to write these 4 limits. Okay? You want to say what happens as x approaches positive infinity of the function. Okay, that's what you want to investigate or find. You want to find what happens as x approaches negative infinity. Okay, and then you want to find what happens as x approaches the vertical asymptote from the right, okay, of the function, and as x approaches the vertical asymptote from the left of that function. Okay, so these 4 are what you want to investigate when you have rational functions. Okay, again, rational functions are a fraction of polynomials. Remember that? Okay. So these are the 4 things you want to investigate when we have limits involving infinity and rational functions. Okay. Let's look at continuity. Right. So a function is continuous if when you put your pen on the graph, you can trace that graph without lifting your pen from the paper, right? So there's no hole or jump. Here we have a hole, right? So this is a discontinuity. We have a discontinuity at the point x equals c. And here we have a jump, so we have another discontinuity at the point x equals c. So this third graph is kind of like a piecewise function, right? Kind of like what we saw before in the example. A function is continuous, so this is the formal definition of continuity, if the limit as x approaches c of the function is f of c. So right here, right, the limit as x approaches c from the left and from the right is f of c, right? So that is continuous. Here, the limit as x approaches c from the right and the left is not f of c. F of c is this dot, but as I approach from the right and the left, I am approaching this hole, so that is discontinuous. Okay. Same thing here. From the left, it's one value. From the right, it's another value. So there's a discontinuity. Okay. So a function is continuous if the function, if f of c is defined, if the left and right limit exists, and if the value is what you get when you plug c into the function. And sum and differences of continuous functions are continuous. Constant multiples are continuous. Products, quotients, and compositions are continuous. Okay. Polynomial functions are continuous. So for example, if I have 3x squared plus 9x, right? X squared is a parabola, it's continuous. Multiply by 3, that's this rule right here, that's also continuous, right? Because I'm multiplying by a constant. X is a line, that's continuous. Multiplying by 9 gives me continuity. These 2 are continuous functions. Adding them together, that's this rule right here. Sum of continuous functions are continuous. Okay. Rational functions are continuous except where the denominator equals 0, because there you have an asymptote. Okay. Let's look at example 9 in your book. Determine whether each function is continuous or discontinuous. If discontinuous, state where it is discontinuous. Okay. The first one is a polynomial. Okay, polynomials are continuous everywhere. So this is continuous. Okay? That's what the first one says. The first function is continuous since it's a polynomial. The second function, it's a rational function. We know rational functions are not continuous where the denominator equals 0. So let's find where the denominator equals 0. So first thing I want to do is I set the denominator equal to 0, get rid of the square, so I'm going to square root both sides. So then I'm left with x plus 1 equals 0. Then I subtract 1 from both sides, and I get x equals negative 1. So part B is continuous everywhere except for where x equals negative 1. Okay, that's where they got these values. E to the x squared minus 1. Well, we know x squared minus 1 is continuous. E to the something is continuous. Remember what the graph of e to the something looks like? What does e to the something look like? Like this, right? So it's not defined at certain points, but it is continuous. Okay, so the third function is continuous since it is the composition of the exponential function e to the x and the polynomial x squared minus 1. So you want to say for this one it's continuous. So this is what I would write for this one. Continuous where, or continuous on the domain, let's say that. Where it is defined means it's continuous on the domain. Okay. So that is section 2.1. Here are some active learning problems you can do. You can do the odd ones close to these, so you can check your work in the back, and next time we will start section 2.2. Okay, please feel free to get in touch with me if you have any questions. Thank you for watching.